ambil anak lambat sikit, pukul 1. So bolehlah kita proceed kan. Alright, sambil-sambil tu you all boleh submit attendance, takut lupa. I dah turn on the systems. Okay, ada yang dah submit. Okay, boleh sambil-sambil dengar, boleh submit attendance. Okay, this part tu, it's we go for the analysis of sections. Okay. Alright, this is the basic thing is we go as fast as I can. Okay. Alright, so this is the behavior of beam in bendings. Remember, once we apply the load, there will be a bend performance here, bend curve here, especially at the bottom one. So if you zoom up, okay, there will be elongations here. The bottom one in tension, it becomes increase the length, while the top one, it compress. That means it becomes shortens. Okay, there will be cracks here. Okay, that shows that this structure in a stress conditions. Kita bila stress, ni kat dahi ni berkerut kan. Apa ni? Kalau stres, ada yang stres dia makan banyak kan. Kalau saya stres, saya tak selera makan. Ada yang stres, makan ni. Dia nak lari dari masalah. Dia tak nak ingat masalah. Itu pun puncanya. Itu kalau manusia stres. Kalau concrete stress, because it have to support all the loads. Right, that's why there will be a signs of cracks here. Okay, that means this is a signs of the stress, which is because of the concretes, especially at the bottom one. Remember, for this concrete, we have a centroid and also the neutral axis that separate between compression and tension. Remember, concrete is very good in compression, not good in tension, because this tensions is the weakest part of the concrete. So that's why the cracks, the stress will occur initially will occur first at the tensions area. So that's why we provide the reinforcement to help these regions, this area, okay, to support all the loads, to support all the stresses within this weakest part. So that's why we put the longitudinal reinforcements at the bottom side here. Okay, so that is how the beam react with the stress, how why the steels and concrete is a good combinations. Then for the continuous beam, ni kalau simply supported, only one bendings. Okay, kalau continuous, there will be many spans, okay, for the bendings here. So ada yang apa ni, bends upwards, some of it bends upward, downward, and also upward here. Okay, if you look at here, this span by span here, from columns to columns or from support to supports, the bends upward here, there will be a positive or negative directions, right? So ada yang upward, ada yang downward here. The downward here, we call it as a, if I'm not mistaken, we call it as a sagging. Okay, this is, we call it as a sagging. This is hogging. Hogging part. This is sagging, hogging part, sagging, and hogging part here. Okay. This is how the continuous beam reacts. Okay, resists all the load. So that's mean there will be tensions at the bottoms, tensions at the top one, especially at the support here. If you look at here, this is the initial cracks. So in these sections, if I make it as a cross sections here, neutral exists. So that means this become tensions area, and the bottom one become the compressions area. Okay, so that's why we will put the reinforcement at the tensions area within the columns here, because the top one becomes the tensions, while these sections here, okay, these sections, the bottom one is a tension, the top one is a compression. So that's why cracks occurred first at the bottom. So that's why we provide the reinforcements, okay, between the support to the support. So that's why we provide this reinforcement at the bottom one. At the intersections of the column here, because the top one becomes the tensions area, the weakest part of the beam cross section. So that's why we provide the reinforcement at the top one here. Okay. All right. So in designs, this is all the assumptions that we considered for the design. The first one, we considered that all plane sections remain plane. It doesn't matter how high the load, how lower the load, the sections still in plane, still remain plane, still maintain as a B multiple with D. Kita tak consider dia dah sengit sikit ke, dia dah pecah crack ke. No, we just ignore about its effect. We just design based on B multiple with the D, which remain plain as a rectangle section or as a circular sections or square sections. Okay, then the second assumptions here, the strain in bonded reinforcement ataupun pre-stress, okay, in tension or in compression is the same as that in the surrounded concrete. The strain, okay, remember the combinations, the composite between concrete and reinforcement, you punya strain for tensions and then strains for compressions, reinforcement is still the same once it's surrounded with the concrete. Okay, tensile strength of concrete is ignored. Why? Because tensile strength is the weakest strength of the concrete. So we just ignore about the tension strength. We just focus about its compression strength. So that's why for the concrete, we just test the concrete for the compression, because we want to know what is the strength of that concrete, that the best performance for the concrete, right, in terms of its compressive compared to the tensile strength. So that's why we just ignore the value for the tensile strength. Then the stress in the concrete in compressions are derived from the design stress strain curve. Remember, we have a stress strain curve, stress strain curve for the concrete track. So we design based on this stress strain curve. We also have a idealized, right, a curve for the designs. The stress in reinforcements are derived for the design curve. Kalau concrete ada stress strain curve, same goes for the steel. Also, we refer dia punya stress strain curve. So from it, we will come out with its strain for the concrete, which is 0.0035, and also strain for the steel, which is 0.00217. Okay, so this is in details, which is once you apply the loads before deformation or after deformation, it's still the same surface. It still B multiple with the D surface. Okay. The cross section does not distort out of plane during deformations, which is kalau before deformation, it still have a compression, tension which exists. After deformation, at failure or anything, it still as the same plane surface. Okay, so this is stress curve. Okay, for concrete, thread for the steels. Remember, you punya strain for the concretes is 0.0035, and then for the steel is a 0.00217. Okay, based on the FCK, based on the FYK. So if this FCK is bought the original 100% of FCK, but for the design, which is FCD, we consider for the concrete 0.567. Apa dah? 0.5. Betul lah, 0.567 FCK. Kalau steel tadi untuk for the design, which is 0.817 FYK. Okay, so you need to remember and understand all the values here. Okay. All right, so for beam cross sections, okay, once we come out with stress and strain distribution, it will be like this. Okay, this is the value here actually is from the strain gauge. Okay, which is you can plot what's the strain for concrete. This is epsilon is a strain, right? FCC is a strength, FCD strength for the designs, FCK is a idealized, right? Okay, so for the strain for the concretes, which is at the top surface, you can plot here what's the value here, and then once it becomes at the neutral axis, that is divide between compression and tension, the value of strain is equal to 0. Okay, and then for the E for the steel, kalau concrete tadi dia punya strain dia adalah 0.0035. Kalau steel 0.00217. So that's mean for the concrete here 0, the maximum one here. The maximum one here, the 0.0035. This is start with 0. Okay, so this becomes 0.0035. Then you can plot the neutral axis. You punya strain adalah kosong. Okay, and then for the steel, this is start with 0 strain. The maximum of the steel is a 0.00217. Okay, so kalau kat sini dia punya steel adalah 0.00217. Okay, then once we make it as a stress here, okay, and then this is the curve here for uh, the designs, and then this become the simplified for the cross sections, okay, which is you need to understand these cross sections here. This stress strain diagram, we call it as a stress strain diagram here, okay. um, this is like stress, okay, that referred for the concrete stress. And then this is the lines which is that referred to the force of the steel here. This is the force of the concrete that we assumes at the center of these rectangle shapes. So that means there will be a FCC, which is FCC, and then there will be a FST here. Okay, sorry, kalau FST, it should be exactly at the reinforcement, which is, this is FST. This is FST. So, kalau lukis balik, this is the neutral axis. Okay, so you can just draw, this is one line, that means starts from the zero. Okay, this is the reinforcement, so that means this is the surface of the concrete. So make it as a one rectangle shapes here. This is the neutral axis. So FCC is located at the center of these rectangles, which is, this is force for the concrete, while this is the locations position for the steel. So this is in line with the level of steel, which is FST. So this is how we draw, okay, the distributions of the stress and strain blocks. Okay, so you can go through. We have these three kinds of stress strain blocks. The first one here, so ada bentuk triangle kan. So this is the distributions applies when the stress are very nearly proportions to the strains. Okay, which generally occurs at the loading levels encountered by under working loads. It used at the serviceability limit state. So ni dalam masa dia punya services. Okay, so this is how the stress blocks diagram is. Okay, the second one, it become curve here. Okay, dia daripada sini dia berubah jadi curve kat sini. Okay, this is the rectangle. We call it as a rectangle parabolic stress blocks. Represents the distributions at failure. Ini masa services, during its services. Okay, during its lifetime, it supports all the loads. So, then the next here is a stress box that represents once the structure at failure. Okay, once the structure at failure, when the compressive strain with the plastic range is associated with the design of ultimate limit state. Ni dah di sini adalah serviceability limit state. This becomes ultimate limit state. It almost at failure. And then this is the end of it, which is simplified from the ultimate here. The equivalence rectangle stress block is a simplified alternative to a rectangular parabolic distributions. Okay, so ni ada curve kan, susah nak kira. It's about mathematicals, analysis. So that's why for the EC, it's simplified from this parabolic, from this curve becomes one rectangles diagrams here. So if you look at here, this is the concrete, which is FCC. This is the steels, which denoted as a FST here. There will be we call it as a lever arm. Lever arm. Kalau bahasa Melayu kita panggil lengan moment. Okay, so that is Z value here. What's the height here? And then what the height also for this block, which is S. Ni tak nampak actually X here. Okay, so you can calculate what is the moment at this point by FST force multiply with the Z, with the length. You also can calculate what is the moment at the bottom at FST by multiply FCC, the strength of the concrete, multiply with the Z, with the length of it. You will know what is the moment at this point here. Okay, there will be other parts that actually you will use this analysis of beam cross sections. So that's why you need to understand the developments from the cross sections once you apply the load, how the stress strain block diagram becomes. Okay. So, kalau lihat sini tadi, ini during its service lifetimes. This is at failure, at ultimate dia punya limit states. This is simplification from this ultimate state, from this failure diagrams. Okay, which is this will be referred in the designs. So if you look at here, how also we get of this for the concrete and also for the steel is actually according to the proportions. Okay, this is the beam sections. Okay, which is you need to do some exercise on how to draw it. Firstly, you just need to make one line, straight line here. Okay, and then extend slightly according to the strains of the concrete. And then remember for the concrete, at neutral axis, the concrete is equal to 0. So that's why you will get of this kind of rectangle, triangle shapes. And then for the steels, right? So this is start from 0. This will be have a value here. This start from 0, and then this will be the maximum value here. This is the strain for the steel pula. Sebab sini adalah level steel. Okay, this is the area for the compressions concrete, which is this part. Compressions will resist all the forces. This area for the tensions, the weakest part, the reinforcement will resist all the loads that apply on that beam sections, right? So that's why the top one we focus on the strain for the concrete. The bottom one we consider the strain for the steel reinforcements. So then you can just close this loop here. Okay. This is how we draw the strains diagrams. This is the strain. Okay, so just make it as a portion here, which is this is the height for the top one, which is X. Okay, so ECC divided by X. So that's why ECC divided by X for the top portions. For the bottom portions of these triangles, okay, which is EST divided by D minus X, right? The length here is D minus X. So that's why a strain of the steels divided by D minus X, which is this is the bottom one, This is the top one. Berapa dia punya X, right? This is X, this is strain for the concrete. Okay, this is dia punya height dia adalah D minus X, which is this is ES. Okay, strain for the steel. You divide by it and then replace of this value for concrete strain, value for steel strain here. Then at the end, you will get off these equations, this value. Okay, make it x as a unknown here. Okay, make it x as an unknown. Then replace EST 0.00217, and then replace concrete 0.0035. You will get x is equal 0.617D. This value is very important, which is that refer to this x. We can control this x here. Okay, so once you have this value of x, which is 0.617D, which is D is a depth, okay, from the beam section. This to ensure that the reinforcement, the steels can achieve its yielding point, can achieve its yielding strength. Kalau steel reinforcement not achieve its yielding, that means it not have a transition from elastic to plastic. It still not utilize all the strength, all its properties. So make sure, so that's why we want to make sure that the steel achieve this limit, achieve this yield strength. In order to ensure that achieve this yield strength, the X value here, the length here should be 0.617D. Okay, that is what it's mean in the stress blocks diagram here. Okay, so because we have a linear or non-linear stage, right? We have a linear lines, we have a curved line here. You can go through in details here. So for the failure, okay, for the failure, we have these three types of failure. Okay, this is important for you to understand. We have beams that is to be designed as a balanced sections. Okay, we have under reinforced sections, we have over reinforced section. Based on this neutral axis value, okay, this is neutral axis value, right? Because we want to ensure that steel reinforcement achieve this yield strength. Itulah dia punya apa kekuatan untuk steel. We depends on the yield strength. Okay, so based on this X, it should be 0.617D. So that means this is the benchmarks. There will be a X less than it. There will be a situations that is more than 0.617D, right? So this is the benchmark here. Okay, ada case yang akan kurang, ada case yang akan lebih daripada benchmark ni. Biasalah tu kan. So that's why depends on this X. We can determine these three types of failure. Okay, look at one by one here. Once X is equal 0.617D, that means this is the balance designs. Okay, balance failure. Okay, kalau you lihat these beam sections, let's say ada two bars of shear reinforcements. Okay, so once you apply the loads at time of the failure, the concrete reach its strain limit. What the strain limit for the concrete? which is 0.0035, right? Then the steel also achieve its strength limit. For the steel, it's a 0.00217. Concrete tadi 0.0035. Ni dah banyak kali ulang Strain for concrete, strain for the steel. At time at the failure, okay, the x here, the neutral axis is equal to 0.617 D. What is D? The depth, okay, the depth of the beam sections. At these times, the concretes and the steels serentak simultaneously here, okay, achieve its ultimate state, achieve its ultimate strength limit for the concrete and also for the steel. Dia serentak. Dekat atas pun crushing concrete, dekat bawah pun dia achieve the yield limit. That is balance. Balance design. Berapa numbers of reinforcement yang you nak provide in order to ensure that that beam section categorized as the balanced designs. That means at failure, it will fail at the same time. It will reach the ultimate state at the same times between concrete and also the steel. Then for under reinforced, that means once the X value less than 0.617D. So kalau balance tadi serentak, kalau under reinforced, that means the steel will fail first. Barulah continue with the concrete fail, concrete crushing. Dia tak serentak. Okay, so that means the steel achieve its strength limit first, which is 0.00217, and after that, followed by the crushings of the concrete, followed by the failure of the concrete. You can imagine how the numbers of reinforcement that you provide. Okay, how the reinforcement that you provide. Might be this one is just nice. Steel reinforcement, let's say 2H, let's say 2H20. Just nice. It fail simultaneously at the same time with the concrete. So then another engineer designed as under reinforced, which is you reduce slightly the numbers or might be the size of the reinforcement. Let's say 2H 16, might be 2H16. So the same load, okay, the same load that it applied, this is still 100 kilonewtons. And then the same load that is applied here, about 100 kilonewtons. So you can think logically. So once you apply the same load but different arrangements, or once you reduce a bit slightly the diameter, the size of reinforcement, so that means the steel here will reach its limitation first, will reach its yield strength, the strength limit, then after that followed by the concrete here. Okay, so that is mean by under reinforced flexure failure or under reinforced designs. For over reinforced, once you provide the reinforcement more, right? So it becomes axial. Axial, it changes, which is more than 0.617D. Okay, once it's more than 6.17 here. This one's axial, the axial, dah penat bila X kat sini kurang, dia bila kurang dia bergeraklah ke atas, bila dia lebih Neutral axis ni bertambah lah ke bawah. So kalau I lukis exactly, so X ni katalah dah kat sini. Okay, this is the length of the X here. So this is apa ni, reduce, mungkin kat sini X. Ni balance, sama atas dan bawah kan. So kalau over reinforce, that means you provide more reinforcement here. Katalah letak 4 bar kan, you provide nak pergi kepada safety ni kan, you provide for H20 which is over reinforced. Once you provide the over reinforced more reinforcement here, that means at the same load, okay, once applied of 100 kilonewtons, okay, they still not reach its yield strength. Dia banyak kan, dia masih relax, steady lagi, resist all the loads. Dia belum sampai lagi limits untuk fail for the steel. Tapi concrete, but concrete is still the same portion, it's still the same grades. So that means concrete will fail first. Okay, then concrete will fail first, then barulah followed by the steel reinforcement. For the rules of failure, once the concrete fail first, that means all for the whole structure fail. Walaupun still belum fail. So which means this kind of over reinforcement is not permitted. So it's not permitted. We go for this under reinforced. Okay, look at for the performance of the steel. Once it's achieve the limits, achieve the yield strength. Okay, I lukis balik the characteristic of steel. Once it achieves the yield strength here, okay, it still can go further, right? It still can perform. It still can utilize all of its dia punya strengths and so on. So that's why for the concretes, okay, if I draw for the concretes, once it achieved the maximum, it dropped here, so it failed here. Okay, so there's no longer performance after the maximums here. Okay, rather than the steel. So that's why once the steel fail first, that structure is still in the safe conditions. Okay, it's still in the safe condition, because after that the concrete will take the turn, okay, to proceed to resist the loads. Okay, kalau the first failure, dia serentak, concrete fail first, steel fail also at the same time, so there's no extensions of the lifetimes, okay, compared to the under reinforced. Okay, kalau over reinforced, once the concrete fails, so that means that structure is failed enough, although that still not achieve its limitations. Alright, faham ke tak? Bersungguh-sungguh ni. Can you understand me? Habis dah kan? So this is how the load deflections, okay, for under reinforced, as you can see here, and for over reinforced. Kalau under reinforced, which is the steel fail first and then barulah concrete, it still can extend its service lifetime here. Okay, the deflections can be longer. Okay, but what happened for over reinforced? So at here concrete fail without the steel yield. So dia dah fail dulu concrete, dah achieve it concrete's limit. So still just macam merugi sajalah kan. We provide all the reinforcements inside the beam sections. It just wastes the cost because it not utilize its strengths to support all the load. Sebab concrete dah fail dulu. Okay, so that's why we not go for the over reinforced. We will design based on under reinforced beam. We also not go for balance because it fail simultaneously, okay, at the same time. For the based on the design, based on the strengths of concrete, based on the strength for the steels. So that means we have these limitations, right? Which is X is equals or less than 0.61 D here, which is according to the balance and also under enforced. But EC2, it give another extra precautions. It give you another allowance, another safety, which is it reduce the neutral axis value here from 0.617D. In a design, we have to refer 0.45D. Okay, so easy to make another reductions for the safety allowance here. That's it. Thank you. Okay, so that's it all for part 1 and part 2. Make sure you do your revisions because another part we will proceed for the design. So you can faham this basics first, okay, before we go for the calculations for the next weeks. So that's it. Any questions? Please make sure you submit your attendance. Okay. Any questions so far? Senyap, tak ada soalan lah kan? Senyap je. Okay, Mas Turul. Faham, tak ada soalan. Alright, so I stop right here. See you again by next week. Okay, thank you everyone.
Thank you, Doctor. Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.
Okay.
Thank you, Doctor.
Terima